Three transformations, TA, TB, TC, are represented by the matrices A, B, and C. And we're given A and B, and I have to find the matrix which represents the inverse transformation of TA. So that is A minus 1. And we're going to get 1. I mean, you could just put this in your calculator. It's quite quick to find, like, without. It's only 1 mark here. It's going to be 1 of the determinant, which is 1 times 3 minus 0 times 2, so 1 over 3. And then let me find the adjugate matrix. So that's when I cross out, if I want to find the first row, first column, I cross out these, and then I'll be taking 3 up here. And then the next one, I'll cross out the 0, and I'll take the 2, but it's going to be minus 2, because we're in the first row, second column, so it's minus 1 to the power of 3. Or you might just remember the plus minus minus plus. The next one, I'm going to get 0. Actually, don't need the minus because it's just 0. And I'm going to get 1 here. But don't remember, don't forget I need to transpose it. So my final answer is going to be a third 3. We swap along this diagonal. So we get 3, 0, minus 2, 1. These are some sort of transformations. We're asked by consider a matrix multiplication to determine whether TA followed by TB is the same transformation as TB followed by TA. So TA followed by TB would be the matrix BA, because you always start from the right and work your way to the left. A bit like with functions. Do G first and then F. So 1, 0, 0 minus 1 multiplied by 1, 0, 2, 3, which is going to give us 1, 0, minus 2, minus 3. And let's do TB followed by TA. One, 0, 2, minus 3. So AB is not equal to BA. So not the same. I don't want to write the whole thing out again. These two are not the same. Not the same resultant transformation. We're then told that transformations R and S are each defined as being the result of successive transformations as specified. Explain using a property of matrix multiplication why R and S are the same transformation. So for transformation R, we are doing TA followed by TB. So TA would be, well, A would be on the right, and then would be followed by B, and then it would be followed by C. Whilst for S, we've got TA, so A applied first, and TB followed by TC, the CB in a bracket. And what we can say is that CBA is equal to CBA, which we then just normally write as CBA, since I think when I did it, I just said they're the same. So R and S are the same, but technically we should say since matrix multiplication is associative. i.e. the order doesn't matter. You can do BA first and then times by C on the left, or you can do CB first and then times by A on the right. So therefore, T and S are the same. A quadrilateral Q has vertices D, E, F, and G in anti-clockwise order from D. So I'm just going to draw some sort of quadrilateral. So we could have D here, for example, and then E, F, G going anti-clockwise. Under transformation R, Q's image, Q dash, has vertices D dash, E dash, B dash, and G dash, where D dash is the image. And the area of Q in suitable units is 5. We're then given that the determinant of C is a squared plus 1, where a is a real constant. We're asked to determine the order of the vertices of Q dash, starting anti-clockwise from D. So what I need to look into is the determinant of this C, B, A. Now, there's a little fact that you should be familiar with, and that is if you find the determinant of 3 matrices multiplied together, it's the same as the determinants found separately multiplied together. So for C, we know it's, so I know it's a bit hard to read this, I'm just trying to fit it all in. We know it's a squared plus 1. For B, it's going to be minus 1. And A we found before was 3. So I'm going to get minus 3 times a squared plus 1. And we're told that a squared is a real constant, so this is necessarily going to be less than 0. And what that means is if the determinant was positive, the orientation would stay the same. If the determinant is negative, then it swaps around. We get like a reflection going on. And therefore, starting anti-clockwise from D dash, it's going to be D dash followed by G dash. See, these two swap around. And then F dash, that stays where it is in the order, and E dash. That is our answer here. We're asked to, find in terms of A the area of Q dash. So to get the area, you multiply your original area by the determinant. So the area, ignore the negative now because the area is going to be a positive quantity. It's going to be 15 because it's 3 times 5 times a squared plus 1. And then finally explain whether the inverse transformation for R exists, justifying our answer. So I'm going to fit it into this little gap here, part 3. Now, for the inverse of R, we would find 1 over the determinant of CBA. And we know it's never going to be 0 because a squared plus 1 is positive. So I wrote down the determinant of CBA is, well, I actually said it was greater than 0, but all we need to say really is it's not equal to 0. I mean, it's the same thing. And that means the inverse will exist. There we have it. Quite a little technical question. Quite like it. Hope it all makes sense.